In this video, we're going to look at the quiz question, the challenge for the first week of the course. And we're given here a specific survival function, and we need to do certain calculations with this survival function. And first of all, we need to explain why the given mathematical function is a valid survival function. So that implies that we're going to look at the following concept. So we want the survival function to start for t equal to 0 from 1, right? And if you plug in t equals 0, in the above expression, you'll get 105 divided by 105 to the power 1 over 3. So that is indeed equal to 1. So do remember that this survival probability evaluated in t equals 0, that is the probability that the random variable t0 will be strictly larger than 0, and that indeed should be 1, right? As a next thing to verify, we want the survival function. If t goes to plus infinity, so if we take the limit for t going to plus infinity, our survival function should go to 0, because then we're looking at the limit of the probability for t going to plus infinity, the probability that t0 is taking a value above t. So if t goes to plus infinity, that probability should go to 0. And indeed, if you let the t here take the largest possible value, and in our given example here, the largest possible value that t can take is equal to 105, right? So if we plug that in the expression, then we'll see that the survival function evaluated in 105 equals 0 divided by 105, and that's indeed 0, right? So two important conditions are already verified, are checked. Our survival function starts from 1 and goes to 0 if t becomes large. And then the last thing to check is that the survival function, the S0t, should be a non-increasing function of t. Now, how are we going to check that? We can look at the derivative with respect to t of our survival function. And if we work out this derivative, what do we find? We'll find 1 over 3 multiplied with minus 1 over 105, and then we'll get 105 minus t divided by 105 to the power minus 2/3, right? So what do we see? That this always takes a negative value for a t between 0 and 150. So because our derivative always takes a negative value, the corresponding function here, the survival function that is given, is a non-increasing function. So if you verify these three conditions, you are convinced that this is indeed a valid survival function. Now, if we move on in the exercise, the next thing we need to do is we need to calculate with the given survival function the life expectancy of a newborn. And we're talking here about the complete life expectancy of this newborn. So what are we going to do? We're going to calculate in number 2, we're going to calculate the expected value of the positive and continuous random variable t0. And we're going to do that, and that's a formula that we discussed in the course, by taking the integral from 0 to plus infinity of tp0 dt, right? And remember that what I denote here with tp0, that is my survival function evaluated in t. That's the probability that my random variable t0 is larger than t. So what am I going to do? I've got the formula available for this survival function. So the only thing I need to do is take the integral of this expression, right? So I'm going to go like this. And I know, of course, that the upper bound is not going to be plus infinity here, but I'm going to take the integral up to the value of 105. 105, right? So what do I get if I start working with this? This is the integral from 0 to 105 of 1 minus t divided by 105 to the power 1 over 3 dt. Okay, and now I can do a change of variable where I could say, okay, let's denote with 1 minus t divided by 105. Let's denote that as u, right? So what I get then is u to the power 103, and then the minus dt divided by 105, that's equal to du. So what is my dt? So that is dt, that is equal to minus 105 times du. So that's what I can plug in over here, minus 105. And then I need to think about my boundaries. So if the t starts from 0, then the u starts from 1. And if the t is equal to 105, then the u is equal to 0. All right, so that's the expression that I get. And if I work out the whole thing, I'll get minus 105 times u to the power 4/3 divided by 4 divided by 3, between u is 1 and u is 0. So that gives me minus 105 multiplied with 3/4 with a minus. So in the end, I'll get 78.75. And that's the life expectancy, the complete life expectancy for a newborn whose survival function is following the given function over here in the exercise. As a last or as one of the final steps, we need to calculate certain probabilities here given in actuarial notation. So we're going to look first of all at the 10q30. So that's a probability of dying. It's the probability that a 30-year-old will die within 10 years from now, right? So that means he will die between age 30 and age 40. So one way to calculate this is by switching to the complement. That's 1 minus the 10-year survival probability. So that is 1 minus the probability that t30 is larger than 10. And now I'm going to make the connection between my t30 random variable and my t0 random variable. So we've discussed that in the class. So given that the t0 is above 30, what's the probability that t0 will then also be above 40, right? So that's exactly the same probability, and I'm doing that because now I can use my survival function that is given for my 0-year-old, right? So now I can use that guy and plug it in over here. So what do we retrieve? It's the survival function of a 0-year-old evaluated in 40 divided by the survival function of the 0-year-old evaluated in 30. I'll plug in the numbers, and you can do that yourself. You'll eventually see that that becomes the following expression. So that is equal to 0.0465805, right? And once again, it's the probability that a 30-year-old will die within the next 10 years. And to conclude, let's look at the last question. So here we are asked to calculate the probability that a 40-year-old will die between ages 65 and 75. So we can write that as a deferred mortality probability. So you look at a 40-year-old, right? A 40-year-old, he or she will first survive until age 65. And then you ask yourself the question, what is the probability that this 40-year-old will die between age 65 and age 75, right? So that's what we're going to do. And we've discussed in the class that you can see this as a difference of two survival probabilities, namely the probability to live another 25 years as a 40-year-old minus the probability to live at least another 35 years as a 40-year-old, right? So if you want to sketch that on a timeline, you can do it as follows. So we're looking at somebody who's 40-year-old at time 0. So this is time and here is age. And we want to know what's the probability that you die between age 65 and age 75. So that's between time point 25 and 35, right? So I want to know what's the probability to die here in between. That's the probability that I'm looking at. And I can see that as I'm going to take the probability to survive another 25 years. That's the blue guy. And I'm going to subtract the probability to live 35 years or even more. And that's the green probability. So if I look at these differences, then I'm exactly able to calculate the probability that I'm looking for. So what we can do now to calculate this expression is we can use the link with the survival function, of a newborn. And that's in fact what we've been using here as well. So here we also had such a survival function. And here survival probability, and here we saw that you can see that, or you can rewrite that using the ratio of two survival functions for my newborn here, right? So we're going to do something similar over here, and we'll retrieve S0 evaluated in 65 divided by S0 evaluated in 40 minus then S0 evaluated in 75 divided by S0 evaluated in 40. So if I do the maths, then I'll eventually find 40 to the power 1 over 3 minus 30 to the power 1 over 3 divided by 65 to the power 1 over 3, and that is 0.0777685. So that's the answer for this last part of our question.